I'm going to start with a little bit of history, just like Katie did. And okay, is this working? There we go. So this is probably a little bit further back in the past, maybe 2 years after I was born. Satellite imagery that was first collected from the Corona mission. Long time ago, not very high quality, but it was sort of amazing because it was imagery from space. And that provided a level of worldwide transparency that enabled people half a world away to see what was going on the other side of the planet. However, that was something that was only available to a very small number of people in a very small number of governments. The image that you see here was something that was published in Aviation Week, and it was really pretty sensational because these sort of images had not been available to anybody outside that very select group of people. So what led me to start DigitalGlobe was, why not make that available to the rest of the world? And so we're going to talk first about what's available today. Well, here's what's available today. This is where we are. This is an image that was actually taken a few weeks ago because I needed to get the slide deck in ahead of time. But we collect these sort of images on a very current basis, and we'll talk about what that means in a moment. DigitalGlobe has about 1 billion square kilometers of imagery collected in our archive. That's close to collecting the land surface area of the planet about 7 times over. And in large parts of the world, that means that we have hundreds of images collected over particular areas. This is a map of part of the Ukraine, and you can see the red areas correspond to north of 150 images taken within that region. The other characteristic of modern constellations, modern satellite constellations, is that we can pick and choose where we collect, so that in general we can collect the images of the places that are the most interesting without being constrained to just take what happens to be below the satellite. This is a pass, one satellite pass over Thailand, and the yellow dots that you see there correspond to where we've taken images. So this is effectively giving us the flexibility that if we want to see a particular part of the world on a frequent basis, we can do that. Here's another example. This is slightly speeded up. It's a single satellite pass over Rio, and we took an image here about every 8 seconds or so. So you can see as we're flying over, the buildings appear to be leaning from one side to another. That's because the satellite's going from one side looking down to looking down the other direction. You can also obviously see the traffic on the airport. That building lean is important because, as I'll talk about it in a little bit, the fact that satellite images are collected from a variety of different angles means that it's not as easy for a computer to look for things like changes as it might be for a human. That agility that I talked about, which enabled us to collect more or less wherever we wanted to collect in that pass over Thailand, and which also allowed us to collect that sport mode photography of Rio Airport, also lets us collect very large areas. This is a shot of the three satellites worth of imagery that was collected over Haiti in a single day following the earthquake. The yellow is Worldview 2, the blue is Worldview 1, and the green is QuickBird. DigitalGlobe, as I'll talk about in a bit, hosted imagery of Haiti, put it up very rapidly for access on the web. But the point here is that we were able to collect an entire country in a single day, and then we went back and collected it over and over and over again. You've also, I think, appreciated that the resolution of imagery that you can see is pretty impressive. This is an image of a McDonald's, and turns out it's 6-inch resolution. For anybody who happens to be from the U.S. government in the audience, I have to caveat this by saying this was taken from an airplane, not a satellite, because we're only allowed to release imagery from satellite that is 50 centimeter or about 20 inches. We can't do any better than that by U.S. regulation. But we can fly airplanes as low as we want. If we want to go count nose hairs with airplanes, we can do that. So let's talk about some imagery applications. I'm going to start with accuracy. By accuracy, I don't mean the resolution of the pixel. I mean, how well do we know where that image is on the ground? Getting back to that whole idea of location, how precisely can we locate a pixel in that image compared with where it really is? On the left-hand side, you can see the statistics that we collect from one of our satellites, Worldview 2. The accuracy is between about 4 and 5 meters for a single image that's unprocessed. Perhaps a more interesting number is the relative accuracy, which is within one of these large images, how accurately are the points in that image related to each other? That turns out to be probably a lot more relevant for mapping. And the accuracies that we're seeing here are definitely less than a meter, in fact, less than a pixel. This particular example, which is pretty typical, is about 0.43 meters. Then when we throw additional processing in using some statistical techniques, we're able to drive those accuracies down even further. The example you see on the left, which looks like a bunch of measles, those were hundreds of images that we statistically processed to generate a much more accurate aggregate view of the ground. And we're able to see accuracies that are on the order of 1.5 meters. And that's without using any additional measurements. So there's nobody sitting on the ground with a GPS receiver saying X marks the spot. This was done totally from the satellite with additional ground processing. And what's nice about these techniques is the more imagery we add, the more accurate it becomes. So why should anybody care? Well, here's an example that was pulled off Google Maps where you have road data that's laid over an image, and the roads don't line up with the image. If you can imagine some emerging applications like automated driver assistance systems where you use the location data to enhance driver safety, having that kind of inaccuracy is a bad thing. It's the difference between being on the road and off the side of a cliff. So accuracy from satellite imagery provides a base layer that you can register a variety of other data sets against. And when you're starting to see accuracies that are on the order of 1.5 meters, now all of a sudden that imagery becomes quite usable. I'm going to switch gears from accuracy to talking about color. The most recent satellite that we launched, WorldView 2, has, in addition to the 4 colors that people are used to with satellite imagery, which are a red, green, blue, and a near-infrared band, we have an additional 4 colors, a coastal band, a yellow band, a red edge band, and then a second infrared band. And that gives us sort of a CSI from space-like capability, but without the soundtrack. What does that mean? So we can look at a traditional red, green, blue image. This is an image of a coastal area taken with WorldView 2. You see the green on land, and then you can see the water. What I'm going to do now is flip through a snapshot of a series of images, all from one image, but they're different color bands. So we're going to start with the infrared, and what you can see here is wave action and some of the linear reefs, but you're basically looking at stuff that's on the surface. And now as I flip through the additional bands, you start going deeper. You're seeing some of the submerged aquatic vegetation. Now with the coastal band, which is all the far end, now you're seeing actually the bottom of the ocean. Now this is down to a depth of about 20 or 30 meters. So what? So we're able to use that to produce bathymetry maps, depth maps, and we're able to see accuracies that are on the order of about 1.5 meters. So that's useful, for example, in parts of the world where every time a storm blows through, the bottom of the ocean changes, like the Caribbean. One of the key enablers for us is the ability to take advantage of advances in gaming technology, specifically graphic processing units, and use that for performing the truly massive amounts of calculations that you need to do when you're working on an archive that has 1 billion square kilometers. And think about how many pixels that is when you think that 1 square kilometer at half-meter resolution is about 4 million pixels. So lots and lots of pixels. We have, this is our prototype node, the first one we built in our basement in Colorado. This is about a half a petaflop system, and it's 5 racks of equipment. A couple of years ago, that would have actually qualified as a supercomputer. I think it probably still fits on the list, and that's actually just a small piece of the total puzzle. What can we do with that? We can achieve speed-ups in processing of geospatial-type imagery because it's a massively parallel problem that are something like, in this particular case, a factor of 47 over a CPU. And this is not a sort of a toy number that ignores all of the nitty-gritty of I/O and loading and storing data. This is an end-to-end speed-up. So we were able to, in an end-to-end fashion, process elevation data, extract high-accuracy elevation data from satellite imagery nearly 50 times faster than you could with a traditional CPU. Another example of an application is change detection. So here we're flipping through a before and an after image of Concepcion and automatically identifying the areas, in this particular case, where you've had mud washing over the green space and roads. Here's another example of an oil spill, or rather an oil tank that's spilled. You can see before and after image, just watch as it sequences through. That's before, That's after, and then this is the automatic identification of changes. Remember what I had said, that part of the difficulty with identifying changes when you have satellites that are looking from a variety of different angles, it's easy to identify the change. The problem is most of those changes are irrelevant. They're because the buildings are leaning over. What we've been able to do is apply some of that processing capability to take out, for example, the building lean and just identify the changes that are material. So this really leads me to the last part of the talk, which is seconds to anywhere. And I'm going to start with why is imagery important for mobile? I think you've all seen examples like this. This is from Central Park. As we go zoom in, this is what the map would show. This is what the image would show. So the imagery provides a level of richness and detail that is not present in even a fairly highly annotated map. And you think about it, that makes sense because the fraction of the Earth's surface that's covered by roads is a vanishingly small. It's much, much less than 1%. It's a fraction of a percent. And maps generally have focused on things like roads and big objects like buildings, whereas imagery gives you the detail of everything that's in between. So one of the things that is part of this seconds to anywhere is the ability to get that imagery out to a variety of users, whether they're mobile or fixed, and do so via web services. Now, we've been doing this for probably the last 3 years. We acquired a company back in 2007 called Globe Explorer that made imagery available via web services. And we are in the process of, right now in beta, and this summer we'll be rolling out a second generation of our geospatial cloud that has really 3 elements. One of them is the content library, that billion square kilometers. The second is web services, which I'll talk about in a moment. And the third is a global content distribution network. We have, for example, as part of that beta, we have a node up in Europe that is reducing the latency for European users for accessing our data from on the order of 10 seconds down to a factor of 10 less than that, like on the order of a second. The web services that we provide, follow the commonly adopted standards. Those include all of the OGC, WFS, WCS, WMS services, and they're designed to allow for imagery to be integrated in pretty much any of the geospatial applications that are out there. So as an example of that, going back to that Haiti example, when we collected our imagery, we immediately stood it up on our crisis event web service and made that imagery available to relief organizations around the planet. And that was started January 12th when the earthquake happened. Within a few hours, we had the crisis event service up and running. Imagery, once it was collected, was available on that service within a few hours. And by January 25th, we had over 4,000 users around the planet who had access to something like 130,000 square nautical miles of imagery of the region. And that, by the way, included not just our imagery, but imagery from other sources as well. Although something like about 93% of the imagery collected over Haiti in that, as a result of the response came from DigitalGlobe, and about 7% came from other sources. And so that really is the essence of seconds to anywhere. It's the ability to collect imagery anywhere on the planet and make that imagery accessible over the web to users in a variety of applications, and do so in a way that those applications have the ability to get at the imagery in seconds. And with that, I'll thank you.